Okay. So I've uploaded lecture 16 to you, and so we begin with lecture 17. And this time I will be talking about, we had talked about phase diagrams. There are two types of phase diagram we discussed. One was phase diagram for binary eutectic system, which all involved two pure phases in equilibrium with the melt, and the two mineral phases that didn't form a solid solution. And in the next one, we had A and B components that formed two phase components of a single solid, forming a solid solution. So we have done that, and now I will tell you a little bit about how, this is fine as far as you can see that this is fine as a logical conclusions that we have drawn. But what is important is to realize, how do we understand these processes when we look at rocks? When we look at rocks, how do we understand these things that they have happened, or what are the physical manifestations from which we get a lot of information? And this is what we called an analysis of igneous textures of igneous rocks. Textures of igneous rocks, like you have the texture of my shirt, not the color, the texture of my shirt. So what are the texture? We will talk about the textural relations between crystals and melt, and we will try and see and understand it in terms of phase diagrams. So our topic for lecture 16 is textures of igneous rocks and here I will introduce you to a concept of what is called equilibrium versus fractional crystallization versus fractional crystallization. This is a very important concept. In equilibrium crystallization, whether it was involving pure phases or whether it involved solid phases, two pure phases in equilibrium with the melt, or a solid solution phase in equilibrium with the melt, what we assumed or we considered at the time, that crystals crystallize from melts, and there is across the crystal melt surface, the contact plane or the interface between the crystal and melt, there is a constant change in the composition between the crystal and the melt. There is always a little mass transfer that is occurring at very micron scales between crystals and minerals, crystals and melts. But sometimes, where the crystal isn't physically with the melt and is interacting, there could be situations where the crystal is physically cut off from the melt in a way that the crystal melt communication is completely lost. Crystal melt communication, the change of material across crystal and melt, that is lost. And then we try and find out what can be done. What can be done about it? How does it manifest it? We never see an igneous rock forming in its process because the temperature is very high and it just burns everything around. So we only see its effects. So what we are trying to find out, the features that tell us that whether the rock was an equilibrium crystallization or equilibrium melting or fractional crystallization and fractional melting. What is it all about? Now, fractional crystallization is a process by which minerals are not allowed to communicate with the melt. Have you understood? Let's understand it. You can understand it better during crystallization. So we will talk about crystallization first. So you have a melt and you produce a crystal, and the crystal by some method, some way, is not allowed to interact with the melt any further. There can be multiple reasons. We will talk about the reasons, but we will see what happens then. Now, we drew this diagram last class, last lecture, where you had A and B, and let's assume there is something like TMA and this is TMB, and this is A, and weight percent A, for example, increases to 100 here or 0 here. So where you have weight percent A 0, their weight percent B is 100. That's the diagram in which you have AB solid solution, you have a liquid, and you have AB solid solution plus liquid. And as we know, this is called the liquidus, and this one is the solidus. Below the solidus, everything is solid. Above the liquidus, everything is liquid. And you have, in the intervening zone, a situation where you have AB solid solution mineral in equilibrium with the liquid. Now, let's say we take a melt at this composition. So let's divide this. This is 50. This is 25, weight percent A, and this is 75. So let's take a composition which is here, or roughly, see. So this is a liquid L0. What is the composition of liquid L0? Is A25. Now I'm keeping it A25 and not B75. It's obviously, if it's a binary diagram, then if A25, then B has to be 75. It can't have any other numbers. So L0 is A25. L0 is a melt. It doesn't have a crystal. It has a melt where the percentage of A molecules in the melt, A component in the melt, is 25%, and B component in the melt is 25%, 75%. There are no crystals because the temperature is above the liquidus. Now, if you cool this melt, so what happens as the melt cools? Nothing happens except that the melt cools down. The temperature, nothing changes until, for this composition A25, the liquid now has the composition which coincides with the liquidus. When we do this, immediately the liquid, since now AB solid solution plus liquid, they are in equilibrium. So at this temperature, it splits into S1 at temperature T1. At temperature T1, you generate a liquid L0. L1 remains almost at the same, but small amounts of S1 crystals have separated out, nucleate from the melt. And the composition of S1, as you can see, is very B-rich, or maybe the composition of S1 is say A5. That means if it's A5, then it's B95. It's obvious. Now, you have the liquid which now precipitates and it splits into S1. When S1 crystallizes, which is very B-rich, then the liquid composition moves away. so that obviously, because the composition of the solid and the liquid, the total mass has to remain the same, and so we move into a position at another temperature, and which we say, okay, this is T2, and here you have L2, and for that there is a composition S2, and this is the composition, new composition is S2. So S2 now is say AN8, right? Now please remember, your S2 composition is not about 8, composition is 8, temperature of crystallization is T2, the liquid composition has moved from L1 to L2, so the liquid composition L2 is now no more A25, but maybe A28. The liquid composition has changed to A28 L2, and the solid in equilibrium is A8. Now you see, the solid composition is changing its composition from S1 to S2. That means materials are transferred into the crystals, and some of the materials has to go back into the melt. So there is a interaction or exchange of material between the crystal and the melt, so that the crystal composition changes and the liquid composition also changes. Now, the next point, remember last time we drew this line is L0. Now, if I write, this is L0, so let's say L2, L0, this is M, and S2, L0 is equal to N, then M divided by M plus N, that means this divided by this length, this will give you the fraction of solids. Fraction of solid, not the composition of the solid. The composition of the solid is 8. The fraction of the solid is M divided by M0, or L2 L0 divided by L2 S2. That is what is M divided by M plus N. And this gives you the fraction of crystal. Remember, this M here, if I go back to temperature T1, then this M1 here, M is equal to 0. Why? Because the fraction of solid was almost negligible. But when we come to S2, the fraction of solid has increased. So also the composition of the solid has changed from A5 to A8. Now comes an important point. Let's say, by some reason, we will talk of this reason a little later. By some reason, this S2, which is in equilibrium with the melt at this point of time, say for example, I physically somehow take the crystals away and take it out of the system. So what will happen? Or maybe I leave the crystal in the system, but I don't allow the S2 crystal to exchange matter with L2. Have you understood? So, what I have done here has formed a crystal S2 with a small S1 here and a S2 crystal. I form this at a particular temperature T2, but I do not allow the solid S2 to any way interact with the liquid L2 surrounding it. I do not allow the crystal S2 surrounding the liquid L2 to interact. So what will happen now? The contact is lost. It's a divorce. The contact is completely lost. There's no way S2 is interacting with L2 anymore. You can ask me why. I will talk about it why, but let's get the hang of it first. So what will happen? Now, L2, which formed from L0 to L1 to L2, this L2 now behaves as a system by itself. Have you understood? A system by itself. The melt cannot anymore interact with S2. Will not be able to interact with S2 anymore. So this liquid L2 now becomes an individual entity separated from crystal S2. So now what happens? As we cool the system now, and S2 is not interacting at all with L2, so now what will happen? The L2 will move into another position T3 and will crystallize melt, which is now S3. And S3 is somewhere here, and L3 is somewhere here. This is now L3 and this is now S3. Sorry, this is now S3. So what will happen to S3 now? What is it? What will it do now? So S3 has two possibilities. Either it crystallizes as a new crystal, as a neocrystal, new crystal, with the composition S3, which is rich, which is poorer in B. You see S3 here, possibly the composition will be now A10. This S3 will form as a new crystallizate. When it forms as a new crystallizate, you can form S3 as a new crystal. Have you understood? Or else there can be another possibility that this crystal, you know, S2 is not reacting with the liquid anymore. So what happens? S3 forms a layer on S2. So this is your S3. This is not because of a reaction between S2 and L2, no, because S2 did not react with L2. But S3 can form as a layer or a coating around S2. So S3 can form as an independent crystal, or it can form as a coating on an early formed crystal. Have you understood? Now, which is easier? You know, like mothers give, you know, to nucleate a crystal, is energetically not very easy. There are many reasons for it. It's energetically not very easy. But, if you have a substrate, S2, which is not reacting with L2, melt, but it forms a substrate with a structure, S3 can easily form a coating or a layer around S2. So what happens? The crystal grows from S1 to S2 to S3, but the composition of the crystal is no more uniform. Have you understood? So it's very common to get crystals having a layered structure. So if this continues, as you will be able to imagine, that if you go radially away from the center of the crystal outwards, you will see in all direction A is increasing. A is increasing. This means if you have such a crystal where the composition of the crystal continuously changes, this can only be done by fractional crystallization. Can only be done by fractional crystallization. That means this crystal was formed by small steps of equilibrium, breakage of equilibrium, another equilibrium, breakage of the equilibrium. So it's sort of beheaded equilibrium crystallization. Beheaded equilibrium crystallization. One layer over the other layer, one layer over the other. But inside does not interact with what is outside. These are called zoned crystals. Zoned crystals. Zoned crystals are typically formed by crystal fractionation processes. Are typically formed by crystal fractionation processes. And crystals that do not show zoning, these are formed by equilibrium crystallization processes. Have you understood it? This is very, very crucial. Zoned crystals means these are chemically zoned crystals. The composition of the crystal, composition across the crystal continuously is changing because the crystal within is stopped from reacting with the melt. And then an outer layer is produced, and then again that outer layer is stopped from reacting. So it's like an onion peel. You know, one layer over the other layer, one layer over the other layer, and inside it is not interacting. So zoned crystals are examples of crystal fractionation. But crystals which are not zoned are possibly solid solution crystals, that do not show zoning, are possibly formed by equilibrium crystallization processes. This is one important texture that I have told you. The presence of zoned and unzoned, chemically zoned and chemically unzoned crystals. Chemically zoned crystals are formed where equilibrium crystallization are interrupted at different stages because of crystal fractionation, where a crystal is not allowed to interact with the melt. That is why zoning is done. But when the equilibrium crystallization is continuous and there is no interruption of that equilibrium system, then the chances are that you will have chemically homogeneous crystals. Just a moment. Now I can tell you a few processes. Some of them are quite tricky to understand. I will give you some ways in which equilibrium, this crystal fractionation happens. The processes by which crystal fractionation happens. This is the next point that I will discuss. Let me draw a phase diagram. I will draw it a little carefully because it requires to be drawn carefully. Let's say there is a phase diagram like this, and I am writing here names of two end members. I will let you know. And this is again weight percent albite. Here it's 100. This is temperature of melting of AB, and this is temperature of melting of AN. Okay. Now, before we go into details, there is a mineral called plagioclase. Your teacher in mineralogy should tell you more about this mineral, but for me, I take a mineral which is called plagioclase. The plagioclase mineral phase has two components. One is called albite, and the other one is called anorthite. This is what I wrote as AB, and this is what I wrote as AM. Albite and anorthite. So the formula for albite is Na Al Si3O8, and the formula for anorthite is Ca-Al2 Si2O8. This is the formula of albite and anorthite. Albite I will yes. This is the formula of albite and anorthite. Here you see, if you look at the two formulas, here you have NaAl Si3O8, and here you have Ca-Al2 Si2O8. So if this forms two components of a single phase, then the way the composition changes is Na1 plus Si4 plus is equal to Ca2 plus Al3 plus. Look at this. This is called a coupled substitution. This is called a coupled substitution. This composition, if this forms the two components of solid solution, then there has to be a vector of change which will make this composition to this and this composition to this. How will you do it? If you replace, here it sees sodium and here you see calcium. So if you keep sodium here and calcium here, if you take one sodium plus one silicon, one sodium plus one silicon, so one silicon less means this will be Si2, and here you write Ca2 plus and Al3 plus, so one aluminium is added here. So if you have this, then here it will be Al, one more A, this Al was there, one more Al is added, so this becomes Al2, and you took away one silicon from here, so this silicon 3 becomes silicon 2. So this is a substitution mechanism by which these two end-member components can change the composition in the phase. This is how the mineral plagioclase changes its substitution. Now you can ask me, what is coupled substitution? This will be a little difficult for you, but I have told you important. The sodium occurs, the sodium and calcium occurs in a particular site in a crystal. particular site in a crystal. And aluminium and silicon, you see 1 plus 3, this total is 4, and 2 plus 2, the total is 4. This is another site in the crystal structure. So this is one site and this is other site. So Na replaces calcium in this site. So this change is in one site, Na and Ca. But in order to keep the charge balance, another coupled substitution has to be induced so that Si changes to aluminium. So that is why, because one substitution in this on NaSi has to be coupled with another substitution in another crystal structure, another part of the crystal structure. That is why it is called coupled substitution. This type of substitution is very different than I have told you about a mineral olivine. Say for example, I will just write it in. I have told you about a mineral olivine. You know this mineral now a little bit. And it has two components. One is called forsterite. And the formula is Mg2SiO4. And the other end member is firelite. And this end member has the formula Fe2SiO4. Now you see. What is the substitution by which forsterite changes to firelite? Very simple. Mg2 plus is replaced by Fe2 plus. You see here, this and this represents one particular site. But since both magnesium and iron here are divalent, you can replace magnesium by iron, and this is in a particular site. It does not affect the other site, which is silicon. So this is called diadochic substitution. Diadochic substitution, where substitution only occurs in a particular crystal site and the other sites are independent of it. This is how olivine changes its composition by replacing magnesium by iron and vice versa. But if you have to do that for plagioclase, you can't do it by replacing calcium by sodium because there's a charge imbalance. And because of this charge imbalance, something else has to be changed in the crystal structure so the crystal is electrically neutral. And that is why you have this is why it's called coupled substitution. So you have diadochic, D-I-A-D-O-C-H-I-C, diadochic and coupled substitution. These are the two dominant substitutions by which minerals change their composition. Now, typically, if you look at plagioclase crystals, many of these plagioclase crystals in magmatic rocks show chemical zoning. In fact, unzoned crystals of plagioclase are quite uncommon, which tells you that if unzoned crystals are common, that means fractional crystallization by which the aqueous zoning, that fractional crystallization is a dominant process rather than equilibrium crystallization. It's a dominant process rather than equilibrium crystallization. That means fractional crystallization is the rule. Equilibrium crystallization is an idealized version. It is very similar to when we were in school, we talked about Euclidean geometry, where you could do it in one plane. Triangle ABC, triangle DEF, and then you find the similarity. That's Euclidean geometry. But when we grew up, we realized that all flat parts of any object is nothing but a part of a very large curvature. So essentially, all surfaces have to be curved in nature. And then we moved over to solid geometry. So Euclidean geometry gives you a very idealized way of looking at things. Solid geometry gives it a much more generalized view of the thing. Equilibrium crystallization is almost a very negligible process in the earth. It is only used to teach essentials. Fractional crystallization happens always. That is why plagioclase and most igneous rocks are found to be so. But there is a very interesting aspect to this. Very interesting aspect. If I draw plagioclase crystal, it has typically a rectangular shape. And if you look, the zoning patterns are very dense at the margins. Very dense at the margins. But inside, the zoning patterns are rare. These zones are very strong at the margins. But the central part of the grain is not so strongly zoned. We need to answer this question. Why is it so frequently that we have these plagioclase crystals, the margins are so strongly zoned, but the cores of the grains are not so strongly zoned? What is the reason behind it? But if you take an olivine, so olivine has a shape like this. It has the shape of a football, more like a sphere. It's not exactly a sphere. It is called a dodecahedral shape. Dodecahedral means it has 12 nice, beautiful faces that makes it resembles like a football. So whenever you cut it, you get some sort of a circular section, to absolute, or sometimes an elliptical section. If you look at these olivines, but these olivines are rarely zoned. If in a rock you get both, if you see olivine and you see plagioclase, you will see plagioclases are almost always zoned. And olivine is almost not zoned. And if it is zoned, most of the olivine zoning is restricted to the margin and very weak zoning, very weak. But plagioclase crystals, they are zoned. The margins are very strongly zoned. But the center of the crystals are much less strongly zoned. From the last example that I drew here on the board, you can understand that in a zoned crystal, the temperature increases in this direction, from the margin to the center. Isn't it? Because from the margin to the center, the temperature increases. Is it not? Because the cores of the grains formed at high temperature and the margin forms at lower temperature surrounding it. So the cores represent high temperatures and the margins represent lower temperatures. It is true both for plagioclase as well as for olivine. But there are distinct differences when we go into the zoning patterns of plagioclase and olivine. And now I will try to explain why this zoning pattern emerges for the plagioclase. Now you see here. If I take a liquid point here, remember, anorthite is a high temperature form. Anorthite has a much higher temperature than albite. Anorthite melting temperature is very high compared to that of albite. So that is why I have shown this in a relative scale. Now, if I have a melt of this composition, then, you see, if I take a point here, this is my L1, and for this, somewhere here, there is an S1. Have you understood? If for L1, for liquid composition, there is a composition S1. Okay? Now, okay, before we go into this, let me tell you the following. If you look at the solidus, if you look at the liquidus of this diagram, this has a very gentle slope. The liquidus has a gentle slope towards anorthite. But as we go towards albite, the slope becomes steeper. The slope becomes steeper. And if you look at the solidus, it is just the opposite. The slope here, you know the slope here is dt by dx, temperature by composition, the temperature versus composition slope. This is steep at the anorthite retained, which is in sharp contrast to the flat slope of the liquidus at this end. Right? If you go to the albite end, the dt by dx slope towards the albite end of the liquidus is very steep. But for the solidus, it is almost flat. Have you understood? It's almost flat. So plagioclase gives you a peculiar type of a binary diagram. In that binary diagram, the dt by dx slope of the liquidus is flat at the high temperature anorthite end and steep at the low temperature albite end. For the solidus, you have a converse relationship with a steep dt by dx slope at the anorthite end and a slight gentle slope at the albite end. Now you see what happens. Remember, we are talking of plagioclase and we are talking of albite, which is NaAlSi3O8, and anorthite, which is CaAl2Si2O8, and we have a plagioclase eventually composition NaCaAl, Si4O8. This is the composition of the plagioclase, and it involves a coupled substitution, where substitution involves replacement of not only sodium by calcium. Remember, sodium has an ionic radius of 0.97 angstroms and calcium, this is 1 plus, calcium 2 plus has 0.99 angstroms. So they can replace each other very easily. But this charge imbalance makes life hell because it triggers a substitution between aluminium and silicon, and both being very robust mineral, which does not allow foregoing its position in society. It does not allow itself to be replaced. It's very stubborn, very strong covalency, and it does not have the weak more ionicity of sodium and calcium. So they're very robust directional ALO-SiO bonds that don't want to budge. Now, if you take a liquid L1 at a temperature T1, you get a substitution where you produce S1, right? Now you see here what happens. If you move the liquid, since S1 is precipitated, the liquid is moved to another composition, and this is L2, and for which, here you see, for L2, the solid composition changes only very little. Can you see? S1, because of the steepness of this solidus, for a large change in the liquidus composition, the solid composition changes only very little. So what will happen? This Na plus Si, Ca plus Al exchange will not be that much affected, especially because this is at high temperature the exchange become easier to facilitate also. Not only because of the peculiarity of the slope, but also because at high temperature, this type of exchanges are promoted. So both because of the high temperature and the peculiarity of the slope, for a large change of composition of the liquid, the solid changes its composition in a very, very small amount. So what happens in the plagioclase crystals, zone plagioclase crystals, the central parts which form at higher and hot temperature, they show almost no zoning. They hardly show zoning. But if we shift our concentration from here to here, now you see here, if this liquid composition is here, then, if the liquid composition is here, if this is say L4, then the solid composition here is S4. And if the liquid composition, the solid composition has to change much more. Do you see that? Because of the slope. If you are here, it's even worse, where there has to be a large change in composition of the plagioclase. Do you understand? So what will happen? And the temperatures are also low. And this is the temperature on this side is much lower than that of anorthite. So obviously this type of exchange, NaSi plus CaAl exchange, this will be much more difficult to attain at lower temperature. That's point number one. And point number two, for a small change of liquid composition, the solid composition changes dramatically. So what happens? The solid composition has to change because of this flatness of this slope. The solid composition has to change over large compositions for a small change in the composition of the liquid. So what happens? At the lower temperature, the NiSi-CiAl exchange is aborted. The moment it is aborted, what is happening? The early crystals do not interact as cooling goes on, because to achieve that exchange you need very high temperatures, but the temperatures are low, and for a small change in composition of the liquid, the change in the solid composition is very large. That is why, because of the lower temperature and because of the peculiarity of this slope or the flatness of the solid, which means a large change in composition of the solid is necessary for a small change in composition of the melt, that causes the plagioclase not to react with the melt, prevents the plagioclase from reacting with the melt. That is why in the plagioclase you see at the margins much more strong, prominent zoning patterns. Very prominent zoning patterns at the margin, but very little zoning at the central part. This is high temperature and this is low temperature. And because of the high temperature and the low temperature, and because of the peculiarity of the slope of the reaction, this does not happen. So what happens? Plagioclases typically are cores are less zoned than the margins. Why? Because of the peculiarity of the slope that I have talked about. In the high temperature, for a large range of liquid composition, the solid composition changes very little because the steepness of the slope. At the low temperature end, the liquid composition slope is very steep and the solid slope is very large. So for a small change in the liquid composition, you require a large composition to change. And this is very difficult to achieve for plagioclase because this requires aluminium and silicon to be exchanged if sodium and calcium has to be replaced. That is why this type of a textural relation occurs in plagioclase. But if you take olivine, then it becomes a little simpler. Why? Because olivine phosphorite, meaning Mg2SiO4, and this is firelite, meaning Fe2SiO4, and this is weight percent phosphorite, that means you're in this direction, and this is temperature, and this is temperature of phosphorite melting, and this is temperature of firelite melting temperature. Here the curves have very uniform slopes. Why doesn't the olivine show zoning? Very simple. Because it's a diadochic substitution. You have to replace magnesium, which has an ionic radius. Magnesium has an ionic radius of 0.66 angstroms, and iron has a radius of 0.74 angstrom. There is a smaller difference, but charge imbalances are not there. So magnesium and iron substitute itself without any change in changing silicon. There is no coupled substitution. So what happens is that because of this slope, which is very uniform sloping solidus and liquidus, the features that you see in olivine are not seen in plagioclase, are not seen in olivine. Only in olivine, you can see at lower temperature, obviously, the diffusion between iron and magnesium exchange between olivine and milk, that is disrupted a little bit. So you have zoning only along the margins of the olivine. But the whole majority of olivine is very unzoned. Why unzoned? Because this olivine MgFe exchange occurs at very high temperatures, much higher temperatures than in plagioclase, and also magnesium replacing iron is kinetically much more easier reaction than the coupled substitution that you see in plagioclase. And the slopes of the liquidus and the solidus are very gentle throughout. There is no sharp changes, inflections in the liquidus and solidus. Okay, we'll continue our discussion in the next class.
Technical.